Okay, we haven't actually talked much about climate variability as such. When we say climate variability, uh, of course, there is a seasonal cycle, and we have talked about a little bit about ITCZ moving, SSTs changing, winds weakening and strengthening during the year, and so on. We talked about the monsoon circulation. Usually, when we say climate variability, we think of multiple time scales. So, year-to-year variability, what is referred to as interannual variability, and then there are slower modes like multi-year, well, El Niño is already multi-year, multi-decadal variabilities, multi-centennial variabilities. When we looked at the ice core record, we saw there are 100,000 year time scales, 41,000 year time scales, and so on related to orbital forcing. I wanted to touch on one particular mode of variability in the climate system that is a natural mode, so it's not related to human anthropogenic greenhouse gases and so on. It's the El Niño and La Niña. Obviously, it's the most dominant mode of variability in the climate system, as well as maybe the most well known. I want to talk about it a little bit because it also directly relates to how ocean heat uptake is being modulated by this region where El Niño and La Niña happen. So let's touch on this a little bit. I have other courses where I go into great details of El Niño, La Niña. For this introductory course, we're going to keep it fairly straightforward and simple. So you remember our basic state, where our climatology, where we said we have northeast and southeast trade winds which caused Ekman divergence. Ekman currents are wind-driven currents. So because of Coriolis pushing to the right in the north and left in the southern hemisphere, we had waters being pushed away from the equator as they were pushed towards the west. So we said colder water comes up when the water diverges at the surface. So we have climatologically cold waters, and that Ekman divergence and water coming up we call upwelling. And the currents that we looked at, like the south equatorial, north equatorial currents, push the water westward, and as the waters are being pushed westward, they are accumulating heat and they are warming. And where the upwelling happens and water is pulled up, now you use your concept of the thermocline. The thermocline is also pushed up, which means the sharp gradient is closer to the surface. So if you think of something like the 20-degree isotherm, its depth as the depth of the thermocline for simplification, which works very well in the low latitudes, then you will see that the depth of the 20-degree isotherm would be much shallower here where the cold waters are coming up, and much deeper here where the warm waters are piling up. So you can see that climatological gradient of the thermocline in the east-west direction. So at the surface we have cold tongue and warm pool, as they are known. So as I mentioned before, with cold waters we get high pressure, with warm waters we get low pressure. So rising air, rainfall here, sinking air and subsidence over here. So we talked about the zonal mean meridional circulations and the Hadley cell associated with the convection and rising motion. But when we open it up like an accordion in the zonal direction, we have these zonal asymmetries where the trade winds are now creating upwelling and warm waters here, and the air that rises and hits the ceiling and goes poleward can also go east-west. So which is what happens here. Rising air is hitting the tropopause and going eastward towards the East Pacific, towards Galapagos, and sinking and then supplying the moisture back, and you have another cell on the other side. So this was this is called Walker cell, which you may have already heard of. Walker was East India Company officer in India during the 1800s and 1900s, and he was a mathematician, physicist, meteorologist. He did a lot of incredible work. So he was bothered by famines in India, and he wanted to figure out if he can predict them or understand why they happen. And using pressure at Darwin, Australia, and Tahiti, down here in the southeastern Pacific, at around 17 south, he figured out that there is a difference. So cold waters, high pressure; warm waters, low pressure. And he figured out that once in a while this pressure difference changes and pressure becomes anomalously low here and anomalously high here. And he showed that when that happens, then the monsoon tends to be very deficit, droughts. Okay, so he didn't know that was called El Nino, and because the pressure centers are in the south, he called it the Southern Oscillation. Only in the 1960s, Jakob Birknes showed that the Southern Oscillation and El Nino are essentially the same thing, and they are this coupled ocean-atmosphere interactions, and since then the name has been changed to El Nino Southern Oscillation, or ENSO. So El Nino is called warm phase of ENSO, and La Nina is called cold phase of ENSO. Where did the name El Nino come from? As you can see here, when El Nino happens, for whatever reason, trade winds can relax and the upwelling reduces and the warm water sloshes this way, and along with it the convection moves with the warm waters. So it, anomalously speaking, there is anomalous rising motion here and anomalous sinking motion here, so you get drier climate, higher pressure here, anomalously low pressure, and wetter climate here. So this was noticed in the 1800s by the Spaniard colonizers in Ecuador, Peru, Chile, and so on. And because of dynamic reasons, this warming, maximum warming happens during I have a chopper going by here. Maximum warming happens in December, January, February. And since the usual temperatures are very cold and warm temperatures felt good, even though they had many bad effects, the Spaniards called it El Nino, as in the child or the Christ child, because they thought it's arriving at Christmas time, so it's like God's gift. Obviously the opposite phase, where trade winds get stronger than normal, upwelling gets stronger than normal, cold waters get colder than normal, cannot be called anti-El Nino, it would be anti-Christ, so we call it La Nina. So this is the Walker cell under normal times, sinking here, high pressure. So this pressure gradient can drive winds because we are on the equator, near the equator. Coriolis is weak, so this geostrophy is weak. So you have westward winds. So this is able to be maintained for many years. Once in a while, for reasons that are not completely understood, the system weakens, upwelling weakens, and waters cannot be held up against Australia and New Guinea, so they slosh towards the east and we get El Nino. And because it's a massive heat source, when it moves, when it's sitting here, it's sending waves, it's creating weather and climate across the globe. When it sloshes this way, it perturbs the weather and climate across the globe. So if we look at the anomalies, so those are deviations from the climatology. I didn't officially define it yet. So here, usually it's cold. During a La Nina, it's much warmer than normal, so that's the sea surface temperature anomaly. There are other anomalies happen, so here it's cooler than normal, for example. Indian Ocean also responds, because when you perturb this circulation, you can see that Indian Ocean's Walker cell is also perturbed, and that's what creates droughts during some El Ninos. And this is how a La Nina looks when winds get stronger than normal, upwelling gets stronger than normal, you get colder than normal sea surface temperatures, and you get greater than normal rainfall over here. So you can this actually it typically tends to be warmer than normal, which you can see a little bit here, but Indian Ocean responds as well, and so does the Atlantic. So the entire weather and climate system is perturbed by El Nino and La Nina. There are many details. I'm not getting into it, but as you can imagine, the thermocline gets deeper during an El Nino, gets shallower than normal during a La Nina, which means upwelling is reduced, which means phytoplankton is reduced, which means fish can be reduced or they may die. Species living on Galapagos, which is a very, very rich hotspot for biodiversity, suffer, but they have evolved to deal with this El Nino, La Nina phenomenon over time. So moving heat sources typically create global anomalies. So depending on the season, here December to January, when the warmest temperatures happen here, you get warm wet conditions here across, you get warm and dry conditions here, you get warm conditions here, warm, wet and cool. And so you can see that throughout the globe there are anomalies, or what are called teleconnections, because they are connections forced from the tropical Pacific. Similarly, during La Nina, December to February, you get somewhat opposite looking anomalies. So you get wet conditions over here, cool, warm and dry, cool and dry, and so on and so forth. There is also summer anomalies. So 6 months before, in July, August, you get anomalies as well. So the Indian monsoon happens during June, July, August. So even though El Nino peaks in December, January, February, so does La Nina, they can affect the Indian Ocean because the movement of the heat source is happening over 6 to 9 months. So even though it peaks here in December, January, February, the anomalies here begin to appear in 6 to 9 months before, at least for the very strong El Nino event. So without going into further details, I will just say that these teleconnections matter because they can bring diseases, they can bring droughts, wildfires, dust storms, fish kills, seabirds die, all sorts of connections, teleconnections happen. So let me leave the El Nino story here and come back to explain why this is critical for global warming as well. As I have already alluded to before, we said the upwelling here, dynamically forced by the winds and Ekman divergence, actually leads to the ocean taking up heat. And if there is an El Nino and there is warming, then ocean heat uptake is reduced. So we then need to understand how this region responds to global warming. I already discussed a little bit, saying that this is warming less or maybe even cooling a little, while this is warming quite rapidly during the last several decades as a part of the increased greenhouse gases. So if this is warming less or cooling, then ocean will continue to take up heat. Whereas if this begins to warm as fast as here, then obviously ocean heat uptake will be reduced. Plus, imagine that this is cooling, warming less than here, then in a trend sense, on long time scale changes, you are also strengthening this temperature and pressure gradient, because if this is warming less than here, then this is getting lower pressure over time, this is getting higher pressure over time, so the pressure gradient is increasing over time. So the winds will be getting stronger over time, which means upwelling will continue to stay stronger over time. So continued ocean heat uptake will be able to modulate global warming. So we will see such a thing actually did happen recently, even though there is lots of controversies about how strong it was or whether it happened at all. It's called global warming pause. So I will explain that in the next podcast. Okay, so this is a quick introduction to El Nino. As I said, there are other podcasts with more details. Of course, there are many videos on YouTube and so on as well, but I'm introducing it here just for the context of global warming. Okay.